So what I'd like to talk about a little bit, kind of an overview of what the potentials for bioenergy recovery from the oxidation of volatile solids in wastewater treatment. I want to talk about some pathways to bioenergy recovery from thermal oxidation, which, although there are a number of types of furnaces, the most predominantly used furnaces in biosolids are the multiple hearth furnace and the fluidized bed. And finally, I want to explain a rather novel and innovative two-stage thermal oxidation system and go over some recent performance testing from this project in DELCORA. So, you know, biological oxidation and thermal oxidation. Now, the word oxidation is a little bit deceiving because we know that anaerobic digesters don't operate in the presence of oxygen. However, it is an oxidation. It's a biological oxidation. So a well-designed, well-performing digester reduces the volatile fraction by about 65 to 70%. I can tell you why that is if you have a question later on. Where thermal oxidation reduces volatile solids by 100%. So in terms of bioenergy production, when you look at digesters, the methane fraction is about 60% and has a heating value, a calorific value, about 600 BTUs per cubic foot. You make about 15, 16 cubic foot per every pound destroyed. That results in about 9,000 BTUs of energy per pound of volatile destroyed. In a thermal oxidizer, you produce heat energy about 10 to 12,000 BTUs per pound destroyed. By the way, a lot of information on co-digestion. There's co-incineration too. The addition of fats, oils, and grease only increases these kinds of numbers. You can use food waste and other, the same volatiles that you can use in co-digestion, you can use in co-incineration. So, I mentioned before, the most prevalent types of incinerators or thermal oxidation devices are multiple hearth furnaces and fluidized beds. Both are capable of meeting the recently adopted MACT, Maximum Available Control Technology standards, issued by US EPA in the States. So I want to talk about the multiple hearth furnace. Some call it the older type of thing, and there's a number of jobs out there. Replace your multiple hearths with brand new fluid bed incinerators. I frankly don't see a need. Both have been used for a long time, tried and proven technology. I mean, multiple hearths since the 40s, fluidized beds since the 60s. The useful life of a furnace can easily exceed 50 years. The furnace is different than the pump or the other system. It's bricks and steel. You have to do brickwork from time to time, but the frequency of that brickwork is no different from a new unit than an existing unit. The multiple hearth is a very ingenious device. I don't know where the pointer went, but what happens in a multiple hearth is the cake is introduced to the top of the furnace. It dries on the upper hearth, combusts in the middle. You have carbon burnout and ash cooling in the lower hearth. It's an ingenious device. It does all of this in one vessel. We talk about digestion in terms of, high performance digestion. Oftentimes multiple steps to do this. This unit does it all in one vessel. Also, the ash from a multiple hearth versus a fluidized bed is bottom ash, so it's dry. In a fly ash system, you have to wet the ash as it comes out of the top of the furnace. One guy told me, Stan, I don't want to dewater twice. I dewater my sludge once, I don't want to dewater the ash. So the multiple hearth has that advantage also. So, with these incinerators, how do they recover bioenergy? Well, in the fluidized bed, it burns in what's called the freeboard or the upper zone there, about 1600 degrees. Typically on a fluidized bed, there's what's called a preheater. They recover some of that heat from the exhaust and pipe it back into the wind box or the bottom of the fluid bed to conserve energy and heat in there. Takes about half the heat, by the way. But there's still enough heat left over to go to a recuperative type heat exchanger. And from there, you can go to a steam turbine or an organic Rankine cycle. I'll touch on that a little bit. I have a lot more information. The multiple hearth, because it dries in the upper zones, picks up undesirable contaminants in the drying phase. So you have to put an afterburner to burn out these VOCs that were stripped out of the drying state. So they put an afterburner, which is basically just a refractory line vessel with a burner in it. Couple second detention time. That heats it up to 1500 degrees to destroy the VOCs. That then could be taken again to the recuperative heat exchanger into a steam turbine or organic Rankine cycle system. But the multiple hearth offers another option, and that is two-stage thermal oxidation, where we come right out of the furnace. So, well, let me just explain the conventional afterburner. So, in the furnace, again, you know, as it dries, it strips the VOCs. You come over here, you burn those out, you go to the scrubber, and this is what's called the conventional afterburner. Now, there have been some modifications to remove the upper hearths and introduce sludge to hearth 3, and that's called the top hearth or zero hearth afterburner. But again, you lose some surface area of the hearth, of the hearth area. That has an impact on capacity. Also, my experience with these types of modifications is that you have to run the furnace at very hot temperatures, and it really does increase the auxiliary fuel. There are custom-made afterburners that you can apply to the top of the furnace to fit the building constraints. There are some of these in operation working very well, but they're fuel hogs. So what is a Rankine cycle? I showed it here with a multiple hearth, but basically out of the afterburner, you go through a heat exchanger. I call it a boiler in this picture. That takes water, converts it to steam. Steam spins the turbine, makes the electrical power. You can recover a little heat in the condenser over there where you cool the steam back to water for a closed loop system. So, this recuperative heat exchanger or boiler is really a tube boiler. People have applied fin type boilers to these applications, and it's the wrong application. The fins plug and corrode and fail. You need a tube type boiler, but it's a straightforward tube type boiler. Steam drum on top, then it goes to a steam turbine, or it could go to an organic Rankine cycle. Just a quick word on organic Rankine cycle. I don't know what's organic about this thing. The fluid, so instead of water to steam, they use a thermal fluid. They call it an organic thermal fluid that has a lower boiling point to go to vapor than water does to steam. It has a lower latent heat of vaporization than water to steam, and it's kinder to the turbine blades, because in a steam turbine, if the steam pressure variates, you could pit the turbine blades, where this is oil, so it tends to lubricate the blades. So it's much kinder to the turbine itself. So, I said it before, the multiple hearth offers another way to do this. Could it be a better mousetrap? Well, I certainly think so. So in the two-stage oxidation system, the first stage of combustion is in the furnace. So now we come out of here with this VOC latent gas. VOCs are not water soluble. They make it right through the scrubber, and we let them go. Let them go right through the scrubber, and at the back end of the scrubber, we put this thing called a regenerative thermal oxidizer. You could use a shell and tube heat exchanger here too, but that's where we do the second stage of combustion. So we allow those VOCs to move all the way through the scrubber, and then reheat them at the back end with a bioenergy recovery system that captures the heat, and I'll show you how this works in a moment here. So in this system, what happens is most of the fuel in any furnace comes from the sludge. You got a small amount of auxiliary fuel depending on your moisture and volatile content. The bulk of that heat is wasted to the scrubber. Small amount of heat goes over to the RTO. The RTO is a very interesting device. It's a heat exchanger and energy recovery system. Those two vertical columns are ceramic packed columns. And what happens in a conventional, you come out of the furnace about 800, 1,000 degrees, but to destroy the volatiles, you need at least 1350, 1450 degrees F to burn out the VOCs. So they heat the exhaust gas out of the furnace from 800 to 1400. Then it goes through the scrubber and it cools down to about 100 degrees. What we did was first take this temperature down to 100 degrees. And then we go to the RTO, we get, call it a free ride, or a temperature rise through that ceramic column from 100 back up to 1100 degrees. We have an afterburner section on the top where we raise it back up to the 1450, same as that. Then it leaves its heat behind in the adjacent canister, so it goes out of the stack at about 300 degrees. People said, Stan, how could this work? By the way, this system was invented by a great combustion guy by the name of Al Battery. But anyway, why this works is, if you look at the delta T, we're going about 650 degrees right here. The delta T is from here to here, so we have 200 degree delta T. So number one, we have a smaller delta T, but more importantly, the gases coming out of the furnace at 800,000 degrees hold 10 times the amount of water that they do over here after they're cooled. Volume of gas is reduced tenfold, moisture is reduced tenfold, so we do not have the heat demand that is associated with the moisture and some reduction in the gas volume. If we look at this on a fuel basis, conventional afterburner, this particular example was for 1400 degrees, required about 9 million BTU per hour. The recuperative or shell and tube heat exchanger about 3,500. The regenerative in this heat material balance was about 1.2. About a 90% reduction in fuel to accomplish the same thing. So this is how it works. It reduces the moisture and the gas volume. That's 90% less afterburner fuel. Also, by the way, there's less fan energy because there's less volume of gas to pull around. A little kW saving there. We can recover the heat recovery, a regenerative 90-95%. You could actually do natural gas injection and bring that up to like 97. Remarkable. The ceramic media goes from 100 to 1,000 degrees and back again in 90 seconds. 24 hours a day, 7 days a week. The ceramic is similar material that they use on a space shuttle, the tiles to protect. So it was really NASA who developed the materials that made this whole thing possible. The other benefits of this is these like the heat exchangers for the organic Rankine cycles, this is nasty stuff, this gas. It's moisture laden, acid gases, metals, abrasives. When we go through the scrubber, we reduce all that. We condense out the acids, we remove the particulate, so now we have a relatively clean and dry gas that doesn't have near the effect on the heat exchanger that like a heat exchanger located right after the furnace would. Also, I could never understand this, but EPA established different limits for new and existing incinerators and different limits for fluidized bed and multiple hearth furnaces. So the mercury emission limits established by the regulations are more lenient for existing multiple hearths, but if we ever had to add mercury to that, the gases coming out of the RTO are just ideally suited for mercury removal. In other mercury removal systems, they have to reheat the gases to prevent the condensation of water on the carbon column. Really, mercury removal is carbon filtration. These systems are just, if the regulations ever go that way, we're in a good position to do that. So, the application of this system was done at a plant, DELCORA, Delaware County, regional, whatever, the quality management authority, Chester, PA, 50 MGD plant, 2 multiple hearth furnaces, 22 footers, 8 hearths. DELCORA, I believe, is the largest truck-hauled waste receiving facility could be the East Coast. It's not uncommon at DELCORA to receive 120 to 150 tractor-trailer loads a day. It's phenomenal. Their truck receiving facility looks like those old drive-in movie theaters. The trucks are just lined up. But, so what, is there a pointer here?
No, I think someone else brought one.
Okay. Well, what basically happens? This is an add-on to the existing system. Before, there's a scrubber in the building, the stacks were right here. Oh, thanks, Bill.
Okay, so Stan, I just tell you right. I realized after 2 months that I made a mistake on the counter. I have 15 minutes that overlap between break and your presentation. So I just ask you to speed it up so everybody else has got to speed up.
All right.
So,
Oh.
my bad.
Existing stacks right here and here. We piped them over to some new wet electrostatic precipitators. The precipitators were put in not necessarily to meet the regulations to protect the media. Here's the RTOs. We put a new stack in here. So we also, inside the building, to get a capacity increase, replaced the scrubber. We put a Quench and a multi-venturi scrubber in there, so gases come out of the furnace about 1,000. We cool them down with the Quench to about 150, and then through the there's a packed bed and multi-venturi scrubber come out about 100 degrees. What that scrubber looks like is this. We come down through the Quench, we spray some water in to cool it, go through the packed bed, spray a little more water in there, rinse the particulate out, then through the multi-venturi sections, mist eliminator, and out. That's what the multi-venturis look like. The wet electrostatic precipitator, very important for biosolids applications. This stuff, again, is nasty stuff. We used a big tube downflow precipitator. What that means is that, ooh, I hit the wrong.
You probably hit the
wrong button there.
power button or something. I don't know.
But so there are other wet electrostatic precipitators where the gases are going up and the water's coming down, and they're smaller tubes. This is ideal situation for corrosion and fouling. Corrosion typically is less prominent when you keep it wet all the time or you keep it dry all the time. When you have upflow, downflow, you get an area in the middle where it's kind of a wet, dry. Downflow is water and air moving in the same direction.
I think we just turned it off, so you have to do your best. We get the thing to come back on.
Okay. So, you know, when considering these precipitators, they're excellent. They remove 90% of the particulate that escapes the wet scrubber inside, and they're very effective in metals removal. And so, again, the precipitator was put in to protect the media. We want to reduce that particulate to protect the ceramic media. Any luck?
I think we have to wait for it to cycle into an on position. Having turned it off.
Okay.
Sorry about that.
So while we're waiting for this, the other nice thing about this was DELCORA was able to operate, because we tied into the stacks after their process, DELCORA was able to operate their incinerators right and build the new stuff independent of one another. And it took about a day or so just to connect that T damper into the final stack. Permitting was not that difficult with Pennsylvania DEP. They were involved, but we didn't have much permit issues, because what we were able to do was reduce fuel and simultaneously reduce emissions. And so DEP was very happy with that. We also reduced maintenance on the furnace, because we could operate the furnace at a cooler temperature. So,
Okay.
Picture of the wet ESPs. Just give you an idea what those things look like outside. Yeah, keep that away from me. I use my finger. So the RTO. This has been done before, but it's the first time anybody ever used a 2 canister RTO. They always use 3 canister. So what happens is the cool gases come in about 100 degrees. They go through here, and there are these poppet valves. When the valve is in this position, the gases are directed up through the ceramic media. The temperature is elevated from 100 up to about 1100, 1200. There's a burner here. We operate this one at 1500. You really don't get penalized in fuel very much for temperature on this thing, because it leaves the heat behind. This poppet is over in this position. The gases go down this way and out the stack. After 90 seconds, these switch, and the incoming gases go up this way and go down that way. One way to explain this in terms of fuel is if you think of it like a pendulum. If you get a pendulum and you drop the ball, eventually that settles down. Well, this is like a pendulum, but every time it hits this point, it gets a little kick. So that pendulum swings all the way, and it's remarkably accurate in real-time operation. There's a picture of that poppet valve itself. It's just a thin plate. We've been operating this thing for a year and a half. Just inspected it. Looks brand new. We'll see what it's like in 5-10 years. During the performance test, we measured the fuel. Those little red, hard to see, but those little red things are afterburner fuel. So between the furnace and the afterburner, you know, I just pointed to some spots on that graph. We ran from about $3 to $5 a dry ton in fuel. Furnaces, and I can give you reference after reference, $150 to $300 a dry ton for solids handling. I'd like to see you digester guys meet that.
Stand. We need to try to finish.
Okay, multiple hard furnace 2 was similar, used a little bit more fuel. The sludge wasn't as good. Performance testing, we loaded the furnace at its designed rate. We had a lower pressure drop because of these multi-venturis. The actual gas flow, we predicted about 1.2 million BTUs. We used about 0.5, about half of what we predicted in the RTO. Also, the gas flow at the furnace was good. This table is just a comparison. What I'd like to call your attention to is this last column. These are numbers measured in the test. Here's the percent of the regulatory limits. We were under 10% of all emissions under the new MAX standards. Multiple hard furnace 2 was very similar results. So some of the challenges we ran into were maintaining the process because they're taking these trucks every day and the stuff's coming down the thing. So before we did the construction, we put a conveyor out the window from the dewatering. They use belt presses. And they get about 25 to 30% solids on the belt presses because they have a paper mill that gives them a lot of fiber. Worked with Material Matters in identifying an outlet for this material during construction. Did a very nice job for us to identify a place where we can take unstabilized sludge. The next thing is DELCORA takes in fog waste and they thicken it. But then they put it in sludge holding tanks. It floats to the top. These tanks are not well mixed. When they pump these tanks down and they hit the grease, the furnace goes berserk. I mean, it's tremendous heating value with this grease. So we're now working on a project to bring that grease over separately because it also goes through the belt press and causes problems with the belt presses. And so we run it through the belt press, or around the belt press, and we're going to drip it into. Part of the job was to put swing pumps to feed the furnace, so we're going to drop it into the auger there. We'll get the heating value without the complications. And I would like to really thank the whole staff of DELCORA, who really accepted the challenge of a new system, and the operators who make it work. And Bill Karch was, like DELCORA's assigned project manager, just did a phenomenal job. With that, I know we have a timeline, so if you have any questions, I'll be here till tomorrow.
Yay! This is like the most embarrassing